All right, so now we're going to take a look at binomial probability distribution, and we already saw that before, and I have to do all this here by like 11:55, so we got like 9 minutes, maybe 11:57, which would be 11 minutes. And binomial probability distribution, we're on slide 27, but we've now done all these. We just did bivariate distributions by two varia, which is a variable. Distribution and covariance, and we also learned about correlation. So covariance, I'm going to just change this here. This is covariance and correlation. And we already saw binomial probability distributions, but I just want to go through it the way the textbook presents it. So properties of a binomial experiment. If you remember, the experiment consists of a sequence of n identical trials. Two outcomes, success and failure, are possible on each trial. The probability of success, denoted by p, and failure, denoted by 1 minus p, does not change from trial to trial, and the trials are independent. So by, again, here we're dealing with 2, and nomial, I think of it as name, or I guess maybe number. So we're dealing with two numbers, and just to contrast that with bivariate distributions, is a probability distribution for a bivariate distribution is a probability distribution involving two random variables, and that's called a bivariate distribution, probability distribution. That's with random variables, with variables where you could randomly be like 0 through 5. How many car sales today? Randomly today we had 3. So the variable is random, and that's a bivariate distribution. And with binomial distribution, we're looking at where it's 2, but it's a situation where the experiment has a number of trials, n, represented by n. There's a number of trials represented by n, identical trials. And there's two outcomes for each trial, success and failure. So I think, like if we just go here to chat for a second, I'm going to start a new one here. And right now we're in Stat Mod 5, Part 2. I'm going to say, what does nomial mean? Does it have any root or etymology? Etymology. I'm trying to, logically understand the phrase binomial, and there's something else to it, probability distribution, as in binomial probability distribution in statistics. And so these little forays, when you're learning, are super helpful, and it keeps you engaged, and you're asking those questions, and you're looking for answers, and you're building upon knowledge you already have and creating like bridges between knowledge, so that when you see phrases, you're not just like, I got to memorize this. What's the difference between bivariate and binomial? But you're like, oh yeah, I remember I researched nomial, and this is what I found. And I remember bivariate is by two variate, variable, two variables, and that's for like two random variables, bivariate. And for binomial here, it came up with nomial itself isn't a standalone word. It's typically found as part of mathematical terms like binomial or polynomial. To understand its meaning, let's break down its roots and how it relates to the word binomial. Roots and etymology. The suffix nomial comes from Latin nomen, meaning name or term. I was thinking nomial, name. And prefix bi means two. Therefore, binomial literally means two terms. And so I don't really need to read more, but that's my definition. And the two terms that we're looking for here, binomial, would be success and failure. And actually, I think this little investigation we just did is totally a success. And I think I'll make these a slightly different color because, I don't know, for me this helps, right? To kind of this is the thing, and then, here are two little things we talked about. So this is what you need to have a binomial experiment. And when you have a binomial experiment, you're going to be able to use this formula right here it's a binomial probability function to calculate the probability of something. And what you're going to calculate is the probability of X successes in n trials. So we're looking at success and failure here. But let's work up to that. So our interest is in the number of successes occurring in n trials. We let X denote the number of successes occurring in n trials. And here, just to keep things consistent with the previous slide, I might do this, right? Successes, because we're really kind of nomial is a name, and there's two names, and it's success and failure. And we did this kind of notation here, and now we're doing this here just to really emphasize this is about successes. And so here's a binomial probability function, and we're looking for the probability of x successes in n trials, where n is the number of trials, x is the number of successes, and p is the probability of a success in one trial. Now, if we had something like this, where we wanted to see out of the next 3 customers, first customer, second customer, third customer, how many out of the next 3 customers, what's the probability of them, like 2 of the customers buying, so there was a sale, a purchase, S, that's the success, and there was no purchase, F, that's the failure. Like here is the tree diagram. So the first customer comes in and they either purchase or they don't purchase, success or failure. And then the second customer, if we went to here, it'd be success or failure. If we went to here in the first, it'd be success or failure. And then for the third customer, we could be at 1 of 4 points after the first 2. And for the third customer, it's either going to be success or failure, depending upon which point we're at. So if you went like, you know, S, F, S, you would have S, S, F, and you'd have 2 successes. So when we look at these 2 successes, there's 3 of those, 1, 2, 3, and there's 8 possibilities. So 3 out of 8, if we do the math on that, 3 out of 8 is 0.375. But what this takes into account is, you know, what this, to do the probability that way would be to say that it's equally likely between success and failure. And we, you know, if it's not equally likely, and so let's say the scenario is that here there's a probability of 0.3 that a customer will make a purchase, we can't just kind of like do the math that way. We have to actually do it like this, where we know the probability of success on one trial. And here we are saying in this example, the probability of success in one trial is 0.3, And so when we calculate that using 0.3, right, we get like, you know, we can do each calculation individually. And so we could say success, success, failure, 0.3 times 0.3 times 1 minus 0.3, which is 0.7. And that gives us 0.063. But we have 3, you know, for one situation where we have success, success, failure. And whether or not we have failure, success, success, or success, failure, success, or success, success, failure, it's always going to be 0.063. So the first customer, the probability of having this would be 0.063. The probability of getting this would be 0.063. The probability of getting this would be 0.063. And the probability of getting this would be 0.063. And if we add up all those probabilities for the 3 possible, we have sample space with sample points, and then we have an event, and out of our total sample space, here's our total sample space. If we just look at the different events in that sample space and the probability, we could add up the individual probabilities of those events, and we could get the probability of all 3 of those events happening. That's 0.189, which is different than 0.375. And so we could calculate the probability that way, or we could also calculate the probability using this formula. And if we calculate the probability using this formula, we also get 0.189. And that's where we have the number of trials, n factorial 3. We have the number of successes, 2 factorial. We have the number of trials minus the number of successes, 3 minus 2. And then we have 0.3, the probability squared. And then we have 1 minus p, which would be 0.7 times n to the power of n minus 6. That's my timer telling me that I've got 5 minutes till I got to get on a meeting. And so we could also calculate that this way, 0.189. So that's the binomial probability distribution. We already went through it. The last thing I'm going to point out about the binomial probability distribution is that if you look at the formula, here's the formula, and then here it is again. This probably maybe looks familiar, and that's because when we looked at combinations and permutations, here's the formula for a permutation, and then here's the formula for a combination. And what was the example that was used for permutations and combinations? I don't remember. You can go back and watch that video. But the combinations is to look at the number of combinations we have, where like, you know, objects taken n at a time. The second useful counting rule enables us to count the number of experimental outcomes when n objects are to be selected from a set of n objects. How many combinations can we have? So that's the formula for combinations right there. And then here's the probability of a particular sequence of trial outcomes with X successes and N trials. So what I'd really recommend that you do, and by the way, here's the explanation that I got from ChatGPT when I asked ChatGPT about, I'm going to maybe have to refresh here. Let me just refresh. When I asked ChatGPT about this question here, right, this tree diagram, and why is that probability not able to be used, and it explains exactly what I explained to you, but you might want to pause the video and read through that. And then I don't know if there's anything else there here, and this is also interesting, so you might want to pause the video here and read through this, and then also read through that. So again, I'll make all these chats available on our course materials in the modules in our course on Canvas, and so you can download the PDF of these chats and read through them if you'd like to do that. All right, that's binomial probability distributions.